So is everybody okay on halfway rectifiers? Halfway. We okay? Yeah. Let me come back while I'm thinking about it, because Joebert came and asked a question about some of the questions on the topic quiz. So some things that you figure, just to make sure you understand what's going on, is sometimes what they'll do is they'll come up and there's questions like this on the test, by the way. I mean, on the real test. So I have an AC voltage source, and we'll come over here right now and just go through resistors. Oh, I need to turn them. I do that all the time. Well, I'll go ahead and draw the circuit anyway. So what we were talking about is, so if I was to come over here and draw a it's coming. If I was to come up here and draw a DC circuit, and I'm drawing a 2 resistor DC circuit. Is it there yet? And then I had a 15 volt source, and this was a 1K, and then this right here was a 2.2K. Could everybody solve that? Everybody okay with that circuit? Well, if this was AC, and this was 15 volts, and then this was 1K ohm, and this is 2K ohms, could everybody solve that? Yes, no. Joebert could now, because I explained it to him. Could everybody solve that? Could y'all solve this? Everybody okay? But the problem is that this is, what's that? Is this RMS? You know, or is this peak or peak? Now the problem is when they give you your answers, the voltage might be RMS, but the answers are all in peak or peak to peak or something like that. So what we could do is we got 2 formulas available to us. Everybody understand the voltage divider formula? What's the voltage divider formula? The voltage that the 2.2K drops. So if I use the voltage divider formula over here, the voltage that a resistor in a series circuit drops is proportional to the total resistance in the circuit. So if I can find the ratio of those resistors compared to the total resistance of the circuit, then I can calculate the voltage drop without calculating current. And it saves me a formula, right? You understand? So I could say, if I call this R1 and I call this R2, I can say VR2 would be equal to 2.2K divided by 3.2K. Of course, now I can drop the K. So right now I know R2 is going to drop about 2/3 of the voltage. I know that without even doing any pulling out a calculator. Right, you understand? And then what we do is that's the ratio of the applied voltage that the resistor drops. So you're back in DC and they say, okay, how much would the 2.2K if we applied 15 volts? And y'all do all this math. Then they say, okay, what if we raise the voltage to 30 volts? Well, you'd go back and recalculate current and all that other kind of garbage, but you don't, because it will drop 2/3 of the voltage no matter what voltage you put on that thing. So we're going to use the voltage divider formula a lot in this class, because most of the time you can do RT in your head, especially when you're only dealing with 2 resistors, right? You understand? And you can calculate the voltage drop without calculating what? Current. So it saves you a formula. And every formula you can save is going to be a lesser chance for you to make a what? A mistake. Then I can come up here and multiply this by the applied voltage. No matter what the applied voltage is, right? You understand? So how much voltage would VR2 drop? 2.2 divided by 3.2 times 15.
10.3.
So it's going to drop about 10.3 volts. But notice, I say, okay, how much would it drop if I raised the voltage to 60 volts? You'd say 2.2 divided by 3.2 times what? Yeah, times 60. That's what's nice about the voltage divider formula. So this is in a series circuit. So what you can do is once you get the ratio of that resistance to the total resistance in the circuit, then we can change the voltage all over the place and you don't have to redo a lot of math. Okay, now what's this answer in? This answer is in what? Well, yeah, it's in RMS. So y'all are right, it's in both. Okay, but it's RMS volts, right? Y'all understand that? So all my answers are in peak to peak. So what would I do? Well, I would take this answer. I'd say my V peak to peak would be equal to 2 times, right, 10.3 divided by 0.707. And now we have our answers, right? Now you could have went ahead and converted this to peak to peak. If you converted that to peak before you even started, right, you understand that, then your currents are going to be in peak to peak and your answers are going to be in peak to peak. So it's up to you, right? And so if I saw all my answers in peak to peak, I'd convert my voltage source into right off the bat. Well, I'd do what? I'd convert it to what? Peak to peak. And then it says, okay, what's the voltage across R1? I wouldn't have to do any more math because I've already got the answer. If they want the answers in peak, then I just wouldn't multiply it by 2. And we do this a lot because when we measure with an oscilloscope, it shows me exactly what's there. It shows me an image of what's there, right? You understand? Our oscilloscope does not measure RMS. What does our oscilloscope measure? It measures peak peak. Y'all understand that? So are you okay? So this is going to happen several times, and I guarantee you these are going to be on tests. And that's why you need to go out there and make sure you do those topic quizzes for each chapter, because some of those questions go right on the test. I mean, exactly the same question. If they're not, they're going to be similar. So half-wave rectifiers. Y'all got any problem with half-wave rectifiers? Actually, this right here, these right here should actually be tabbed over, because we have two types of full wave rectifiers. We have a center tap full wave rectifier, right, which we looked at. It requires a center tap transformer, but it only uses 2 diodes. Everybody okay with that guy? And then what we started working on was what we referred to as the full wave bridge. And of course that shows you how they come up with 2V peak over 5. So this is what we get out of a full wave bridge, right? So this is where we get the 2V peak over 5, right? Because we don't average in 0. This is a center tap rectifier, full wave rectifier. And of course, the biggest problem people have is when they give you the voltage on the center tap transformer, they give you all the way across the line. So if I had a 15 volt center tap or 30 volt center tap transformer, then what are we going to use for our calculations? We're going to use 6 volts for our calculations, right? Because it's only using 1/2 of the transformer at the time. But it would surprise me, even though this class is really small, it would surprise me that somebody in the class, if I say a 30 volt center tap transformer, they'll use what? They'll use 30 volts in their math. Now on a full wave bridge, we get the entire voltage of the primary. And of course it depends on how we do it. We're going to show y'all some neat tricks. And of course here, when we do this, we have to take out for 2 diode rods. So silicone, then this output peak would actually be about 1.4 volts less than the input. That makes sense? Are we okay? So what we're going to do is we're going to wire this up, and this, and you'll see people try to wire it like this. But what you need to do is, this is what I tried to show y'all, is that if we look at the circuit, we realize that all it is this circuit right here. So what I'm going to do is I'm just going to draw two straight lines. And then I'm going to say, okay, do we want a positive supply or a negative supply? If I want a positive supply, then what I'm going to do is I'm going to come up here and turn my diodes in this direction. And then I'm going to come down here and turn this in the same direction. And then I'm going to come over here and do the same thing over here. And what we're going to do is this is going to be our DC right here. Unregulated pulsating DC. And then we're going to bring our AC in. And if I wanted a negative power supply, I just do what? To the diodes. I just flip them around. Everybody okay? That makes sense? So it's a lot easier. If you understand that, it's a lot easier to wire up. So we got our train over here. So first of all, I need 4 diodes. And then yeah, either. So I'm going to take my load and I'm going to come off my common anodes and I'm going to hook it up to the top of the resistor. And then I'm going to come up here and take my common cathodes and hook it up to the bottom of the resistor. I think it's the opposite from what y'all see. And we should be ready to power this up. Are we okay? Are you okay? I'm sorry I interrupted y'all while y'all was talking. So we're going to come up here and look across our oscilloscope. And what's nice, I established the ground, right? I established the common. So if I come up here and hook my oscilloscope up one way, oops, I got to plug in my transformer. I know this is sideways yet. So what do I need to do? Well, yeah, first before we trigger, we need to see the waveform. Right. Now notice, here's my 0 reference. So this is definitely DC, right? You understand that? So what I can do is I can grab this and I can change where my 0 reference is. And that's where this little 1 is, indicating channel 1. So I'm just come over here and make my 0 reference down here somewhere. Okay. Now I still can't see it. I usually put it 1 above. That way I know it's not ever going below. I'm going to come up here and put more volts per division. So I went to 5 volts per division, and that's the best we can do. Okay. And now what I'm going to do is I'm going to bring my trigger in. And just get it inside the waveform, right? And then the scope should sync on that. Now I'm gonna come up here and I'm gonna hook up channel 2, making sure I use the same reference, right? Because we as soon as we plug this in, we've established a ground reference, not a common. We've established a ground. So I'm gonna hook this up on the same side. In fact, 60 cycles, guys, you don't even have to hook up the other probe. I mean the other ground. We'll come up here and put them on top of each other. They're both set for 5 volts. Oops, wrong thing. This is supposed to be across the transformer. Can't do that. We can't measure across the transformer. Can somebody tell me why? I can't measure across the transformer with my oscilloscope. Well, I can't. If I was going to measure across with the other, across this with my oscilloscope, then I would have to hook up a ground right here. I can't hook up a ground right there because I've already established the ground over here. You understand? So once you hook up an oscilloscope, then basically that's it. Now I could do what? I could disconnect my other ground and go across the transformer. Right? Y'all understand? Because what I've just done is I've shorted out that diode right there. I put the same connector on both sides, right? You understand that? Because what you have to understand, this is a piece of wire. Now I'm getting that ground through my oscilloscope, but if I was to come over and click that, what I've done is I've connected a piece of wire right there, right? Y'all understand that? So now I got a short circuit. I burn up my diodes or mess up my transformer. Now what we could do is I could disconnect my ground off my meter and I can move it over to, off the resistor, and I can move it over to the transformer and we can measure it and then we can bring it back. But that's one of the problems we have with a full wave is I cannot look across the transformer and the watt. Yeah. Now we could come over here. I think it'll show us 1/2 of it. Let's go over and see what we can look at. Yeah. So what we're doing here is we're just looking at 1/2 of it, because what we're doing is we're looking and seeing what the diode is dropping. So we're seeing when the diode is reverse bias. And I don't know if we're going to be able to trigger in on that, guys. So this is what we got. So now what we got is our scope probe is across a diode. What the scope shows you when you're across the diode, it shows you when the diode is turned off. Does that make sense? Because when it's turned on, it's only dropping about 7/10 of a volt. See if we can get it to sync. No, we can't. But we can get a good idea. Let's move these up on top of each other just to show you the difference between the input and the output. Can y'all see that? Let me blow this up. Sorry. So we can actually see the difference between the input AC, but we're only getting one alternation and we're only getting it across the diode, right? Y'all understand that? And then of course, this is the actual diode. So we got a pretty good differential. We should have a differential about 1.5 volts, 1.4. Are we okay? So, my input voltage, we got a 12.6 volt transformer. We're all the way across the transformer. It's a 12.6 center tap transformer. We're all the way across it. We're not using our center tap. So what, if I put my voltmeter across this, what should I measure? I'm waiting. Do the math. Y'all see the movie, The Martian? What does he say all the time? Do the math, right?
That's who was stuck on the moon.
No, he was stuck on Mars.
On Mars, yeah.
Yeah, they thought he was dead. And
He was talking back to him in
ASCII.
code.
originally, then they figured out how to program the thing. But if y'all looked at the keyboard, it was in hexadecimal. I can show y'all a keyboard of the shuttle, and guess what base it's in? Hexadecimal. Because they don't have enough, they use so much memory, they don't have enough memory for all that graphics garbage, so you program it in hex. If y'all remember the shuttle, y'all remember the shuttle. Okay, guys, what would we get? Somebody tell me what I should anticipate.
So you say you got these.
Yeah, y'all can come up and look at this if y'all want to come up. It's fine. Y'all can get Milton out of the way. So here we got the cathodes connected together here. We got the anodes connected together here, but where they meet. So here, by the way, where your AC comes in, you should also always see an anode cathode.
Oh,
Yeah, because it's doing AC, so it's got to route in one direction and in the other direction. So notice the center is in different vertical lines, and my AC comes in on the center.
Right.
Yeah, the blue wire. See it? So to me, it's easier to wire up by drawing the two parallel lines. It's easier to wire up that way, but you'll see people try to wire it in a bridge, in that the way it's drawn.
what do you read about?
That's connecting my load. Here's my load over here. So here's where we take our load off. We take our load off the common cathodes. Now what we're looking at to figure out the polarity, we're looking at the one that, so notice here the anodes are pointing back toward the source, so that gives us a positive power supply because they're the ones on the top. So the ones that's on the top determines the polarity. The other ones are just come back through return, right? Does that make sense? So if you look at these guys, see their anodes are pointing, these are the ones that's going to my reference, right? You understand? So this is, I'm calling this common, I'm calling this the voltage. Now what's neat about a bridge rectifier, let me disconnect this ground, is if I need a power supply, if I need a negative power supply, I just change my reference. So I'm going to just go over here and flip this around. So now this is my power lead. So here we got cathodes pointing, and this is the common, right? You understand? So all I did was just change which way so all you get off a bridge is you get a minus and you get a plus, right? You understand? So this is the minus because this is the cathode, this is the plus. Which one can you make common? Whichever one you want to. So here we don't get a ground like we do on the center tap. So the center tap, you're stuck. So you have to swap the diodes around. Here we don't, the ground is established or the common is established on the load side. So you can make the minus common or you can make the plus common. If you make the plus common, then you got a negative power supply. If you make the minus common, then you got a positive power supply, which is pretty good. So you'll see these same things all over the place. This is probably one of the most popular rectifiers out there is the full wave. The full wave is probably the most popular. The full wave bridge has been around so long, and I'll show y'all that. Normally, you won't even see this. This is what you'll see. And you look, it's got two leads in the center marked AC, and the outside one lead is marked negative, the other one's marked positive. Is this a negative or a positive? It depends on which one you make common, right? So the common is established on the load side. So instead of the transformer establishing the common, right, you understand that, your load establishes the common. And all we have to do is just change the common on our load, and we could have either one of them. Y'all want to see that? The problem is how do you check that thing with an ohm meter? But let's show you how to do that too. So the advantage of this is one of the diodes go out. So that would be cheaper than 4 of these.
Yeah, or do?
Yeah. For the same ratings, for the same breakover voltage and for the same current, that is cheaper because they can mass produce those. Here they can mass produce them, but they're doing them one at a time, right? You understand? So this would be more expensive than that, but if one of these diodes went out, this would be cheaper to replace than that. So usually individual components or integrated components are cheaper for the manufacturer, but they're more expensive to repair. Because you just can't replace one thing, you gotta replace a lot, you gotta replace all of them. So these are bridge rectifiers. And you can get them in different sizes depending on the amount of current, so that's a bridge rectifier right there. And this is a bridge rectifier right here. So here's AC, here's plus DC, and here's minus DC. I forgot what this guy right here is rated at, but this would have a pretty good sized diode, and it actually can be decent. So you can get these all different varying sizes depending on how much current you want to put through it, right? And you still run into these. You still run into these discrete components.
So you'll be wiring this up to me, like this?
Yeah, on these guys, if you wire these guys up, you're going to create a short circuit. So on these circuits, you're going before you power them up, I'm going to come back and check all of them. Kind of like back in DC. So, just because very easy to make mistakes for the first time. Once you learn them, you know, it makes a lot of sense. So I just created a negative supply, so I need to shift my ground up or my common up. And all I did was just change my reference, right? Of course, now we got to resync our oscilloscope. There it is. So now we got negative DC. If I wanted positive DC, I just changed my common, right? So I'm going to come up here and change my common over to this side. Now we got positive DC. And these are full-wave bridges. Now, what you have to understand, a center tap transformer, the center tap transformers cost a lot more than the diodes do. So that's why you say, well, it uses more diodes, isn't it going to be more expensive? No, it's going to be cheaper because the transformers are worth the money. I don't know if y'all ever got out and tried to buy a transformer before, but those are pretty expensive, especially when you get into your high current transformers because they got to have so much copper in them. But then again, you'll see center tap transformers used with bridges, and that's what I'll show y'all in a minute. Well, first of all, y'all calculating the voltage for me, right? So 12.6 volt center tap, we're using, well, 12.6 volts, we're not using the center tap. Full wave, I'm fixing to hook my meter up to it. And we're going to see what we're going to measure. Of course, we know the transformer is putting out more than 12.6 volts, right? Because we're not loading it to its capacity. This guy right here is this right here is, this is a 1 amp transformer. So let's say it would put out approximately 1 amp of 12.6 volts if you load it with 1 amp. We're using 100K ohm. We're using 100K resistor. So we're not loading it at all. Let me change it over to, so I got a brown, black, orange. Brown, black, orange. Brown, black, orange. 10K. Don't forget, we start counting at 0. That's a common mistake. Yeah. So this is a 10K. So this is still not going to be close. Well, still our calculations are going to probably be a little low. We'll see. Figuring out how much work we're gonna get out of this thing. We're trying to figure out the DC average that we're gonna get out of this thing. It's a full wave bridge rectifier. Y'all should know the formulas, right? So first of all, we need to go to V peak peak, right? I mean, V peak. V peak would be equal to 12.6 divided by 0.707. What does that give us? 17.8. Then we're going to calculate something what we call V peak out. So if you see that in the formula, this is what we get out over here. So V peak out is going to be equal to 17.8 minus 1.4 volts. The diode drop. We usually in the formula we call this V peak secondary because that's what you get out of the secondary. V peak out is what we get on the other side of the diodes, right? You understand? So the other side of the diodes is minus. So I should explain that. So I think that's the way it's labeled. The formulas are on the formula sheet. So I think V peak out half wave is a V peak secondary minus 0.7 for silicon. V peak out full wave. Full wave bridge. I don't know how that's labeled. Should be minus V peak out minus. V peak secondary minus 1.4 volts, right? Or 2 VF times 2 or something like that. So my V peak out would be what? Hey Justin, you okay, man? So what we got? Okay, so 16.4. So now I got V peak out. Now I can calculate my volts DC. It's going to be 2 times 16.4 times 0.707. So my volts DC should calculate to be what? 10.5. Okay, I'm sorry. I was just thinking, make sure y'all pay attention. So V peak out would be equal to what? 16.4, right? Oh, this is not V peak out. This is V out secondary. I'm sorry. That's what I'm. Huh? Let me undo.
I'll try to stop it down to burn down, but you want to wait so fast.
Okay, so let's go back and do it, and maybe I can do it right this time. So V peak secondary. So we're okay. So V peak secondary would be equal to 12.6, right? Divided by 0.707.
Minus 1.4, that was because of the bridge that we did, right?
Well, what happens is here comes, let's just follow this through. So here comes a negative. We come up through here, we lose 0.7 volts. It comes out, goes to the load, comes up through here, we go up through here, we use 0.7 volts. So we lose 1.4 volts for the diode drops. Kirchhoff's voltage law says the sums of the voltage drop has to equal to the applied voltage. I've lost 1.4 volts through my watt. through my diodes. Yeah. Yeah, if I went it back, so on a full wave bridge, you go through 2 diodes both directions. So what did we come up with here? So we were right. Y'all just got me messed up. So 17.8. And then we're going to use something called V peak out, which would be 17.8 minus 1.4 for the diode drop, right? Okay, what would that be? 16. Okay, 16.4. And this is peak. I should be putting P out here all the time to let you know that's not RMS. No, this is peak. When we calculate 12.6 times 0.707, we are calculating BP. If I wanted peak to peak, I would take that answer and multiply it times 2. But our power supply don't deal with peak to peak because it's only seeing one alternation. It's dealing with BP. So this is why all your DC formulas only deal with what? BP. So we don't need peak to peak. All we need to do is what? Yeah. So now I calculate my DC out. My DC out would be equal to 2 times what? 16.4 divided by 3.14. V peak over 5 times 2, right? So what we got? 10.4. And of course, this is DC guys. But it's an average, right? You understand? Because it goes up to peak and then it drops down, right? Okay, so I'm gonna come over here and flip over and see what my meter says. Do we expect it to be higher or lower? Yeah, why? We're not loading the transformer. I got a 10K resistor over here, right? And that's nowhere near the 1 amp capability of the transformer. So it's measuring 11.8 volts. Are we okay? Is it close enough, even though it don't come out like our calculation? Now, if I wanted a perfect calculation, what would I do? I'd take my dang meter and I'd measure the output of my transformer. Right, you understand? And then I would calculate for that, but we're never going to do that because we understand that our calculations are perfect and our components are not. So if I'd have measured this and it would have been like 7 volts, then that would have been a problem, right? So if I came over here and measured this, I know I got a what? Problem. Guess what I just did? I turned it into a halfway rectifier. I've opened up one of the diodes. So any of the diodes in a full wave bridge, if it opens, you end up with a halfway rectifier. So we ended up with about half of the voltage that we calculated. So if I end up with about half of the voltage that we calculated, then basically, oops, something didn't happen. Then we usually assume what? I still got halfway rectifier. So if we end up with about half the voltage that we calculate, then we assume that it's what? Open yet. And if you want, and also in a full wave rectifier, if one of your diodes shorts, you have a short circuit. So that means it's going to start, hopefully it's going to start blowing a fuse in your transformer. So if it starts blowing, then it's either the transformers are shorted or you've got a load that's shorted or you got a shorted diode, and we'll show you how to figure that out too. So power supplies, these power supplies that we're looking at now are not hard to troubleshoot. It's these dang switching power supplies that's hard to troubleshoot. These linear power supplies that we're working on now is easy to design and easy to troubleshoot. Are we okay? Any question? So what advantage does a full wave have? Well, full wave, the polarity is not determined by how we connect. Well, it is. But to change the polarity, all we have to do is change our reference between the minus and the plus, right? You understand?
That's the thing.
Well, no, the advantage is that it's a cheaper arrangement than using a center tap transform. But another feature is that the polarity is determined by how we connect the load to the bridge. So I can use one bridge and they're there side by side, and one of them gives me a negative power supply, the other one gives me a positive power supply. But I'm going to show y'all something in a minute that's very popular. Now, if I was to come in here and encapsulate this, where I've only got 4 leads coming out of the bottom of this thing, right? Understand that? So let me discard this. And I got a blank slide right here. So what I've got is I've got this full wave bridge, and I'm gonna draw it as a bridge. So a bridge, we would draw it as a diamond, right? You understand? And then I would come over here, and now I would come over here. I'm gonna come over here and put these pointing in these directions, right? And then I'm gonna come over here and put these pointing in these directions. So before I make any connection, what do you know? All the diodes are pointing in the same direction. See that? Now what we got is we got 2 leads coming out of a bridge integrated circuit. These 2 right here are marked AC. And this right here would be marked plus. This right here would be marked plus, and this right here would be minus. But I don't have access to the diodes. How would I check this with an ohmmeter? Now, y'all hear what we have to put our meter on the AC side. So what I would do is I would come over here and I would take my meter. It doesn't make any difference. But if I put my plus over here on my meter, and I put my minus up here, I take my minus up there, then what diode would I be checking? I'd be checking this diode right here. Then what I would do is I'd leave, so notice we got the minus on the what? The plus. Then I would take my plus lead on my meter and I move it right there. Now I'm doing what? I'm checking the other diode, right? You understand? I'm checking this right here, right? You understand? Then what would I do? I'd put my minus on the AC, then I'd put my plus, and then I would touch it to both sides. Right? You understand that? Yes or no? No, what we're doing, and maybe this drawing I'm doing is not really good. Yeah, but I don't want to undo all of it. I just want to do a little bit. So we'll come up here. That's the erase. So what we'll do is I'll use red for my meter, red lead. So what I'm going to do is I'm going to come over here and I want to check these 2 diodes right there. So I'll start off by coming over here and taking my black lead or my common lead on my ohm meter or my set to what? Set to the diode scale, right? Understand that? And what I'm going to do is I'm going to take my black lead and connect it to the plus. So what you're going to find that you're using the opposite lead where you get the power out because the power comes in from the bottom and you're coming back through them, right? Understand? And then what I'm going to do is I'm going to take my red lead and I'm going to hook it. I hope it's not red, Rich. I thought I chose red. I'm going to take my red lead. I'm going to take my red lead, and put it right here. Now what we're doing now is we're checking this diode right here. Everybody okay?
Yeah.
And it should measure what? If it's silicone, it should measure about 7/10 of a volt, right? Probably less because our ohm meter is not putting a lot of current out. 5/10, 6/10, right around there is what it's going to measure. Okay. Then what I can do, it depends on what you want to do. I do this so I don't have to swap my leads right now. Is I come up here, is I take my red lead, leave my black lead up there, I take my red lead, and then I move it over to my other AC input. So which diode are we checking?
That's on the top, right?
So we're checking that guy right there. Okay. Now what I would probably do next is, guys, we check them if they're forward biased. We need to also check them if they're reverse biased. What should we measure if we reverse bias? On most meters, it's going to measure overload. Y'all understand that? If you're not touching the leads with your fingers. So it's up to you what you want to do, but what I would do now is I would shift it around, and I would come over here, and I would take my black lead, so we can finish this up now. So I would take my black lead and hook it to my AC. And then I would touch this, and what would that do for us? Now this guy here is going to do what? Turn off, and we should measure, on most meters, you're going to measure overload on the diode scale, right? Right? And then what could you do? I'm thinking about it. I think there's an easy way to do this. It's been a while since I did it. Then I could take my black lead, and I could come up here and do what? Yeah, that's what we're trying to do. So don't just check a diode. Don't just check a diode to see if it works forward bias. You need to always check it to see what happens when you reverse bias. And now we're checking the reverse bias on this diode right here, right? Right? Okay. Then what can I do now? I could leave that right there if I want to. Then I could come over here and I could take my red lead and move it down to here. So which diode am I checking now? Checking this one. Then what can I do now? I think I need to calibrate my pins. Did I move this? Okay. So what we would do is we would clamp this on, right? And then what do I do? So what we did, we just checked that one. What would I do now? I'll take this one and move it over to the other AC side. And now we're checking which one. And then I would reverse my knees and check for reverse bias, right? What's so strange though, notice on this thing, and this is what gets people confused, that when you're checking these two, on the minus side, you put your red lead on. When you're checking these, you put your black lead on, right? You just go between the two, you just swap between the two ACs. And so you need to make sure, anytime you check a diode, you need to make sure you check it forward bias, and you check it what? Reverse bias. Everybody understand that? Forward bias, it should measure whatever diode it is. I've never seen a rectifier diode, a germanium rectifier diode. I'm not saying you're not going to run into that, but I've never seen that. They're usually silicone. But still, if it's a rectifier, if it is germanium, it's going to drop about 0.3 volts, right? You understand? And then the other way, it should turn off. This meter's kind of weird, but this guy don't show infinity, but you can tell what it shows you because when you open your leads up right here, it shows like 3,000 millivolts. If it checks good in circuit, you assume it's good. If it checks bad in circuit, then you're going to have to isolate it. Y'all understand that? Because these things run through, these guys are power supplies. Power supplies are definitely connected in parallel with loads, right? You understand? So that means if I came over here and took this plus and minus out here, and I hooked it up to a 100 ohm resistor, then we got problems, right? Y'all understand? Now it's probably going to measure 100 ohms both ways because the 100 ohms, it'll measure 100 ohms when you reverse bias it on one of the diodes. So if this thing is loaded, so rule of thumb, if you check a solid state device and it checks good in circuit, you assume it's good. If it checks bad in circuit, then you're going to have to isolate the thing to see if it's good or bad. Are we okay? And that's true even for resistors, guys. So this is a full wave bridge rectifier. So you need to know the names of these circuits, right? So we have a half wave rectifier, and then we have two types of full wave. We have a full wave center tap, and then we have a what? Full wave bridge. Okay, guys, y'all take a break. This is the schematics for the power supplies on the trainers that y'all been using, the suitcase trainers over here. And of course, we know the makeup of a basic linear power supply. And what's the makeup? You'd have a power source, right? Transformer, rectifier, filter, regulator, right? So here's the transformer that we showed y'all the other day. So it's a multi-winding output. It's got a single primary, but it's got a multi-winding secondary. This is the one that you're going to connect to down here. It's a center tap transformer, 12.6 volt center tap transformer. This is the one we'll be using inside the trainer. So I'm actually using the true transformer up here, right? Let's see that. Well, y'all are going to be using a true transformer too, but you're not going to have to have a fuse and everything. We're going to have the fuse and everything that's already in the trainer, right? So y'all see, we don't just hook this up to Alabama Power. We got we got an inline fuse in it, in case we come up and do something crazy. So this is the center tap transformer. It's a 12.6 volt center tap transformer. And depending on what the lab tells you to do, sometimes you might use just one half of the transformer or both. Okay. This is a bridge rectifier, and of course this is a bridge rectifier, but this guy is serving as a full wave center tap. Here's our filters right here. So probably, guys, after resistors, capacitors are probably the second most often used passive device in an electronic circuit. You'll see capacitors all over the place. And normally they're used for filtering capabilities, right? So these are filters. This right here is our regulator. And this is a fixed regulator. We'll talk about those. So this is an integrated circuit. So what do you need to regulate? You got to have a circuit. You got to have an unregulated in, a regulated out, and then you got to establish a common. So these are usually called 3-terminal regulators because of that reason. They only got how many watts? 3 terminals on them. These are positive regulators. The 7812 So 78 series are positive regulators, the 79 series are negative regulators. And then what they do is they give you the voltage. So a 7812 is a 12 volt regulator. A positive 12 volt regulator. A 7912 is a what? Is a negative 12 volt regulator. Now these regulators out here, you see these resistors. These are potentiometers that's wired to act like a pot. So these are variable regulators. These guys out here. The LM317 is a positive variable regulator, and the LM337 is a negative variable regulator. So that's a lot of electronics in there, guys. You still only need unregulated in. So on the adjustable, you need regulated in, unregulated in, regulated out, and then the third lead's called the adjust lead. So notice this lead is the one that goes through the resistors. Of course, this is our watt fuse. This is a neon bulb, symbol for a neon bulb. And so does how does a neon bulb create light? This is really neon. We call them neon bulbs, but the only ones that glow orange are neon. The ones that glow blue are not neon. The ones that glow green are not neon. It's another gas, but we still call them neon bulbs. So most gases, if you shoot electrons through most gases, they glow. And that's what we're doing here. So these guys here will glow orange. So anytime you see that little symbol, you'll see the symbol there, and it's got that dot up to it. That means this is a neon bulb. So it looks like this. It comes in like this, and then we got two plates because they're not actually touching. But what you got right up here, I can't draw, is a little dot. That's the symbol for a neon bulb. They work off AC. They have a high voltage rating on them. So I think that the ones we have is rated at 120 volts. Huh? No, not on AC. On DC it'll work, but it'll only glow on one of the rods. So if you look at this, what you'll see is you'll see two rods sticking up in. And it's going to be, of course, in glass. And I'd have to look at it, but if you put DC on it, only one of the rods are going to glow. If you put AC on it, they do what? They both glow. So neon bulbs just works on the same principle. These guys, we don't call them neon bulbs, but they use mercury vapor up there. And we shoot electrons through mercury vapor, and they glow, right? The glass is the gas is what's actually glowing. By the way, you have to take these things with a resistor. So they have a high resistance. As soon as they gas, as soon as they start gassing or emitting light, their resistance drops down a lot. So you need to protect these things with a resistor, So we wouldn't put it directly across the 120 volts, right? You understand? Because as soon as you turn it on, it'll bomb. Now let's talk about this guy in the top. This looks like a bridge rectifier, but look at the difference between this secondary and look at the difference between this secondary. The top secondary is a center tap grounded transformer. The bottom one is not a center tap. It's not a center tap transformer. And the center tap is being used as connected to common. So, and notice everything out through here is reference to that common. And they got it drawn as a common, guys, but it's not. It's not a ground. It's common. I don't think they bring the ground over. By the way, we could tell that. All we need to do is take an ohm meter and hook it up on the ohm scale, right? And hook it up to the center lead on the plug, and then measure to the ground on the trainer. If it shows 0 ohms, then it is grounded. If it's not shown 0 ohms, then it's isolated. So remember, when you go through a transformer, you lose the ground, right? Because we're transferring energy magnetically. And it's up to the engineer to actually do what? Ground the secondary. But this is one of the most often misused symbols in electronics. Just because you see that symbol, it doesn't necessarily mean it's what? Grounded. So the true symbol for common is just an arrow that's not, arrowhead that's not covered in. And that's why you're supposed to color in the diodes, because y'all understand that. Of course, a lot of people don't, but it's no big deal. Because I have no problem if you do that. I know that that's a diode even if you don't color it. So something's going on up here, because if this was working as a full wave bridge, I would not have a grounded secondary or common secondary, right? Everybody okay? So what's going on? Yeah, that's what they're doing. They're using it as a full wave center tap. But the way it works is if you actually look at the circuit, and if I can get back to my PowerPoint. We don't like that, does it? So let me see, how can I get this thing off the draw? I can't remember how to get it off the draw. There's a shortcut key that I just don't know. So we're looking for Adobe. I don't see it. I think I can't close it right here. I can zoom it. Okay. So if we come up here and look at this thing, undoubtedly I did something right. I don't have any idea what I did. So what we've got is we've got a center tap transformer. And of course the center is the common, right? And then I've got this hooked up to a bridge. Yeah, I've got this coming in here. I've got this coming in here. But, okay, you understand? When I come over here to a load, I hook right there. It don't go across here. It comes up here and does this. And then the loads that I connect down here comes up and does this. You understand that? This makes sense? So when I come up here and this is plus, this will be minus, this will be plus, this will be minus relative to each other, right? Okay, that makes sense? So if I follow this over, this guy's going to be on, right? So current flow would leave here, do what? Which one? So this one's off, right? This one is what? What's our other one that's on? Oh, this is plus. Common is plus. Okay, I gotta figure this out. So if I come into here, let's just come in this way. So what do you see? You see a what? Okay, so this is what I want you to see. I want you to see this. Okay, so here comes in the AC right here. No, I need to go back and look. Something's not working out in my head. Okay, that's the difference. So what we're doing, can you see where we're applying the AC? Okay. So it comes into an anode cathode, comes into an anode cathode, then we have our common anodes and our common cathodes. But yeah, make it work over here. So this guy right here would be turned on, right? This guy right here would be off. So current would come up and leave here, right? And then it would do what? I'm sorry, I didn't want to do that. So come up and leave here, go out the ground, do what? Now what we got to do is just figure out which way the current are flowing through these two diodes, right? So this one right here I marked is off, but this guy right here is on. Okay. Are we okay? Okay. So current would come out here, leave this one, right? It would come up here and flow through this one. It would come up to here, and then it would go back to the power source. Right? Okay? That makes sense? And then current would, we're going to draw it positive, so this will be positive. This guy's going to come over here, go through this guy, and it's looking for common. On this one, it's going to go that direction. On this one, it went this direction. So this is going to see a what? Positive. This right here is going to see a what? Negative. No, something's still not right. Because this is supposed to be my negative supply, because notice this one has both what pointing toward the load. I'm sorry, pointing toward the source. This one has two cathodes pointing toward the source. This right here has what? Two anodes pointing toward. What I'm trying to do is come up with this circuit right here. So we got this circuit right here. Then this goes back to my center tap transformer. And then in parallel with that, we have this circuit right here. And they're both using the what? The center tap transformer. That makes sense? It's hard for me to trace current. Can y'all see the circuit right here? So there it is right there, right? And can y'all see the circuit right here? There it is right there. So what we're going to get right here is we're going to get this. Oh, I'm sorry. Yeah, we're going to get this. And what are we going to get down here? So what we're doing, and what I'm trying to tell you, if you look at a transformer, even though it's got a bridge rectifier, and you see that center tap set common, then it's using it as two full-way center tap power supply. Can y'all see that? Even though I'm screwing up on my current. Are we okay? But can y'all see this circuit right here? Oops, no you can't. Boom! Nobody called me on that one. Y'all know if you put your diodes in backwards, you have a short circuit, right? Y'all understand why? Because they're both force bias and they're across the transformer. So this is why I'm gonna come back and make sure we check these and make sure these diodes are shorted together. You see this do a lot on on electronic circuits that require both a negative and positive supply. So what it does, it saves me a what? It saves me a transformer. So I can use one transformer to get both my negative supply and I can get my positive supply. But it's got to be a center tap transformer. So if I did it with two full-blown bridges and I didn't use them as center tap, then I would have to have two transformers, one for my negative supply and one for my positive supply. So doing it this way, we get both a negative and positive supply. When we look at the trainers, schematics, so here's the telltale sign. What's the telltale sign? It's this guy right there, right? So that's the sign that says this is what. And then I come over here and see that the bridge rectifier is not, the output of the bridge rectifier is not referenced to common. Now look at this one. So this bridge rectifier is referenced to what? Common. This bridge rectifier is not. Right? Now, of course, this is the 5-volt regulator, 7805. So 78 series regulators are what? Positive regulators. 79 series are negative, fixed regulators. We call this fixed regulators, which means they put out a voltage. An adjustable regulator means you can do what? You can vary it over a range. Unfortunately, you can never get down to zero. So if you ever hook up the trainer and you go all the way counterclockwise, you'll see it'll drop down to about 2 volts. And then you can get up to the maximum voltage. So what that means to regulate, I have to have more voltage here than I'm regulating there. Does that make sense? Peak voltage, so on this one, remember your diode is, on this situation, the diode is going to have to drop peak, right? You understand? So when you get the PIV rating, what does PIV stand for? Now the problem we have is that books teach it as PIV, but if you look in a data sheet, you're not going to see PIV. It's usually called the repetitive reverse voltage, PRRM, maximum, I think, PRRM. So we'll bring up a data sheet real quick. All these data sheets, by the way, are up on the Blackboard. So we're using 1N 4001s, I think, but we'll look at a 4001. Data sheets, 1N 40X. So the 4000 series has several versions. So this data sheet covers all the way from a 4000 all the way up to a 4007. Most people call them 4001s, 4002s. That's just the technology. So this is the 4001 all the way through the 4007. So here's the guy right here, VRRM, the maximum repetitive reverse breakover voltage. So the only thing that varies between these diodes is their breakover. Non-repetitive means this guy here can handle 60 volts. But if I put a sine wave on that thing, it's a repetitive voltage, right? You'll understand that. So this guy's rated at 50 volts. The O2 is 100, the O3 is 200, of course, repetitive. Here's our average rectified forward current that we can run out of this thing. So these are 1 amp diodes. But for one cycle of the input AC, this guy can handle what? 30 amps. But that's for one cycle. It becomes very important. If you got AC, you understand the charging capacitor. This is our storage temperature. VF, what's VF? What's VF?
Yeah.
That's the forward bias voltage drop this diode could actually run. So this says this guy right here can run between 0.9 typically 0.9 all the way up to 1.1. When it's running at what? 1 amp, it's at 25 degrees. So all you get when you get into solid state devices, all your data sheets are going to be given at a temperature. And 25 degrees centigrade is pretty standard. So what would that be in Fahrenheit? Mm-hmm. Yeah, I need to get used to saying Celsius. They changed the name. Anybody got it yet? About 77 degrees. So this is pretty standard. We'll look at a lot of data sheets, and just about every one of them that I've seen is usually rated at 25 degrees centigrade. This is the reverse current right here. So if we break this thing over, typically we're going to see around 550 nanoamps. Now, 50 nanoamps compared to 1 amp, it's not too much, right? If we have a junction temperature of 100 degrees centigrade, it can go all the way up to what? So what we're doing is we're measuring the leakage current, right? How much it leaks through the solid state device when it's reverse biased. And that varies with starts with T, temperature. That reverse leakage current varies with temperature. And we'll see this when we break over a diode. We're going to deliberately break over a diode, but we're going to put like a 10 mega ohm resistor in series with it so we won't destroy it. So that's pretty close to a data sheet that we run into on a diode. So what are we interested in? What's the two main things we're interested in? Breakover and what? Diameter. That's the two things we're interested in. And everything else usually takes care of itself. And that's what you mainly use to choose the diode that you want. In fact, if you went to a parts place like a Jamico, that's the only ratings they give is the breakover voltage and the current rating. But they also make available a data sheet, which is really neat, guys. So Jamico puts data sheets up there for every device that they sell. Some of them are not good, but when you look at Jamico, so if you want electronic parts, this is a real good place to go. www.jamico.com. And so you can search, so I'd say a 1N, a 4001, right? We could search, and then it'll come up. So this would be the general purpose diode, right? And then we could just actually go to it. And then right here, what does it say? It says the data sheet. So a lot of the data sheets that you see on Blackboard came from Jamico. I just took off the first page because it don't belong to them anyway. And here's the data sheet. Gives you all them neat curves. So if you got a part and you got a part number and it's electronic and you need a data sheet on it, then this is a good source. Or you can just type it. You can just type in the part number. So we should have done that for some of our diodes. And see if we could get that. Are we okay? Okay, so what comes after the rectifier? Filter. Yeah, good. Now we have two passive devices. What do we mean by passive device? So a resistor is a passive device, a capacitor is a passive device. A diode is an active device. A transistor is an active device. FETs are active devices. Triacs are active devices. So solid state devices are active devices. Resistors, capacitors, and inductors, these are what we call passive devices. Passive device is a device that you can't change its characteristics, its conduction characteristics with bias. So we can't change the conductor characteristics of a capacitor with bias. It's fixed in. It does the same thing no matter what DC level we put on it, no matter what AC level we put on it, it does the same thing, right? Now it does vary its opposition, but it does that according to a frequency, right? So the two most often used passive devices, of course, are resistors. You'll see resistors in any electronic circuit because we usually use those to establish bias. And then the second most often used is a capacitor. And what's the main function of capacitors and inductors? Filtering, right? So in power supplies, we're going to use a feature of this where we're going to try to get rid of that pulsating DC and convert it into what we call unregulated DC. So we get rid of a lot of stuff. We can set up tuned circuits. We can use it to get rid of switching noise. We got big problems in digital where you're loading and unloading all these digital. They're ones and zeros, and they're pulsing all over the place. Well, what happened is when you put a current load on the power supply, it has a tendency to go down, and when you put a current, take it off, it has a tendency to go up. And it happens so fast, and it's away from your regulator, and your regulator can't just compensate for that speed. So we have what we call decoupling capacitors, or basically filter capacitors that get rid of all that switching noise that we would have in a digital circuit. So you get into a computer, I guarantee you're going to see capacitors all over the place, even in your cell phone. If you was to take that off and look at the circuit board on your cell phone, you're going to see capacitors in there all over the place because they're digital devices. What we're going to kind of look at is capacitors in a DC circuit. Because that's what we got here, right? A DC circuit. This is a device that has the ability to store a charge for a short amount of time. In fact, you can charge the capacitor up and you can lay it there and it'll discharge through itself. Because that's just what they are. It's almost impossible for me to don't have a current path through a capacitor, right? You understand that? If I've got two electrodes and I've got something in between them, then I've got a current path. There's no such thing as infinite resistance, right? You understand that, first of all. So the ability to store charges is given in units called farads. 1 farad will store 1 coulomb of electrons with 1 volt wide. So first of all, what's a coulomb? Huh? A coulomb is an amp in not moving. So a coulomb is an amp stored, 6.25 times 10 to the 18th electrons stored. So if it's in motion, we call it what? A coulomb in motion, we call it amps. A coulomb stored, we call it a coulomb. So their ability to store those charged particles, right? Either holes or electrons, depending on the capacitor. A polarized capacitor, that's what it does. Well, all of them store holes on one plate and electrons on the other. So 1 farad would have the ability to store 1 amp at what? 1 volt. So that means that as long as I didn't break it over, if I put 2 volts on there, then it would do what? It would store what? 2 volts. If I put 3 amps, 3 coulombs, if I put 3 volts, it would store 3 coulombs, right? You understand that? So it's relative to the voltage you put across those things. You can think of a capacitor as a bucket. The larger the farad, the larger the bucket. That's basically it. What does the size of a bucket determine? How much water it'll hold, right? So we buy our buckets in gallons. So if you want, so this is the basic makeup of a capacitor. We have what we call plate. And in between that, we have an insulator, which they call a dielectric. And we put these plates really close together. So if I put a positive charge on one side, it's going to try to attract electrons, and I put electrons on the other side, those guys are going to try to pull each other together, right? You understand that? And they'll charge up. The storage capacity of the capacitor is determined by the size of the plate, the dielectric that we use, right? And the distance between the plates. So we can have variable capacity. We don't usually do the dielectric because the dielectric is an insulator, so I can't get into a capacitor and change the dielectric, but we can definitely change the size of the plates, right? You understand? Or we can change the distance between them. So a lot of times you'll see them with a little screw on there, and you turn them, and what does it do? It makes the plates further together, puts them further apart, or puts them close together. What we do to adjust the plates is the capacitor only exists where the plates overlap. So what does that mean? Of course, I can't show this on my video. I guess I could. So what that means is my capacitor only exists where the things overlap. So if I can come over here, my capacitance would go up, right? You understand that? If I do this, my capacitance would do what? Go down. So that we either do two ways. We either adjust the size of the plates just by swiping them over each other, right? Or we adjust the distance. So we just have a little screw that we adjust, and it makes the plates either closer together or wider apart. And then we have the insulator. That means I can make a capacitor. I can come over here with my function generator. And we have what we call straight capacitance. Straight capacitance is stuff that just exists. So anytime you have two conductors that are close together, you have a what? Capacitor. We call that straight capacitance. Or we can control the capacitance by doing what? Yeah, by adjusting the size of the plates, right? Or adjusting the what? Distance. So it means this is the wrong scope probe. This scope probe is grounded, so it might not pick this up. We'll try it. What I need one of these right here. So I might have to go get one, but we'll see. This scope probe here, to prevent it from acting like a capacitor, they bring the ground lead all the way down to here. So the ground is brought all the way to tip. So guys, if you pull that thing off and you say, well, I'm going to use that, you got to remember your ground is sitting right there. So I've seen people blow scope probes up just by accidentally touching this in the circuit, and they got their ground reference over there on ground, right? So they do have little tips you can put on here. So be real careful. They have a little cover that you can slide over. If you lose the cover, get a piece of black tape and do what? Cover that sucker up. Because this is a really nice probe out here. You don't have to, these hook probes are good, but it makes it hard to make measurements inside a circuit. So let's see if we can make a capacitor. Let's see if we can get enough coupling through this tip. Oh yeah. So here's my oscilloscope, and I want y'all to look. All right, these two guys are not touching, right? Okay, I'm gonna just start bringing them close together. Can you see my oscilloscope? So if I adjust the size of the plates and how much it passes through, goes through there, right? And it'll be hard for me to adjust the distance. Yeah, so I can adjust the size of the plates, or I can adjust the distance between the plates. There's nothing common between these. We're actually creating a capacitor, and we're passing the actual frequency. Of course, we can't get away from DC. Let me put this on it. So this is what we're passing. So we're passing the AC through there. So the closer I can get them together, the higher the AC is, right? Couple between these two. Y'all see this, right? Which is pretty neat. And then I come over here and do this. So here I'm adjusting the distance between the plates. Here I'm adjusting the size of the plates. So this is how we can make them variable. So this is a lot of times we do this when we check a scope out. I see if it's hooked up right and I'm using the right channel. I just come up here and touch this with my finger because I'm a conductor. I act like a capacitor, right? You understand that? You ever seen that before? Ain't that neat? Those two things are not even touching, so we're creating a capacitor. Now this is the symbol for a capacitor. And this gets people in motor controls confused. I'd been in electronics in the Navy, and I went for an interview at Motorola up in Huntsville, and the guy opened up an electrical schematic. And this is the symbol for a normally open contact, and guess what I called it? I called it a capacitor, and I didn't get the job. That's a true story. Me and another guy, we both went up there together. He was in the Air Force. He was in electronics in the Air Force. I was in the Navy. And we both answered the same thing. So this is the symbol for a capacitor. Now normally, that's why I like to use this symbol right here, guys. So this is one of the symbols. The other symbol we can use is we can come up here and use this guy. And this is the one I like to use because you can't confuse it for a while. A normally open contact. But you're going to run into both of them.
So when would it be different?
What do you mean? So this is what we call a normally open contact. This is the symbol for a normally closed contact. So it will never see. Well, the designator in the schematic. First of all, if you're looking at electrical print, then odds are it's not a capacitor. If you see it in electrical print, odds are they're going to use that symbol right there, so you don't get it confused. But what we do is we have standard designators for different components on the circuit board in a schematic. So this symbol we designate as R. This symbol we designate as L. This symbol we designate as C. So you have C1, C2, C3, C4, C5, and stuff like that. These guys are going to have a name depending on what relay. So if I got a relay over here and it's called John, then the name of this contact is going to be called John because it's being controlled by that relay. So it's real obvious, if you know what's going on, but especially after you've had controls. So we have these designators. We have U. This is the designator for most integrated circuits. We have Q. This is the designator for most transistors. Now you have to understand, this guy right here has been along, and this is T's. So T's are transformers. So I can't use T for transformers and T for, right, you understand that. So I can't use I for inductors because we use I for what? Current. So that's what they do. They kind of say inductors, right? Or L is the measure on this thing. So C is the designator for capacitors, L is the designator for inductors, R is the designator for what? Resistors, U is the designator for integrated circuits, Q is for transistors. Any more? I'm sure there are. So that's basically what you said. So if it's got C5 out there, then it's a what? It's a capacitor. And if it's in an electronic circuit, then odds are it's going to be a capacitor. If it's in an electrical circuit, odds are it's going to be a contact. But in motor controls, you've had motor control. Right? You give all your contacts names depending on what relay controls the contact. The only problem you got is some idiot calls their relay C. But the contact would be called C, and it wouldn't be called what? C1. So all these parts we have different numbers on. You can look at it. I can bring any printed circuit board up here, and you can see all these designators. The storage capacity of a capacitor is determined by. Oh, I already went through that. So this is basically the way it works. We get these plates really close together. One side it sets up and takes electrons. One side sets up and takes holes, right? This is a positive charge. You don't understand these are holes now, right? You understand. And then you get these things closer together, and your negatives are trying to attract the holes, and your holes are trying to attract the electrons, but they can't get to each other because there's a what? There's an insulator in there, and they just sit there. The problem is that there's no such thing as a perfect insulator. So these things will automatically discharge just by what? Just by migrating through the dielectric. If the dielectric was perfect, then a capacitor would hold a charge forever. But even batteries are not perfect. I mean, you can go out and buy a 1.5 volt C battery, and you can leave that thing up for 5 years, and odds are you come back 5 years, it's going to be oxidized over, right? And it's not going to work because it's going to discharge through itself, because we can't keep those plates totally isolated. And if you got these electrons over here and these holes over here, they're trying to get to each other, and they're going to get through that dielectric. So these guys will discharge themselves. Polarized capacitors, and this is the problem we have. What we're trying to do is we're trying to come up with something that we can make a smaller capacitor with a larger storage size. So we have different metals that like to accept electrons, and we have different metals that like to accept holes. So what we do on a polarized capacitor is we put the metals that like to accept holes on one side, and then we put the ones that like to accept on the other side, and then we polarize the thing. They'll be marked positive. One of the leads will be marked positive or negative depending on which one they are. You don't want to put these suckers in there backwards, because those holes are looking for electrons, and those electrons are looking for holes. You put them in there backwards, and you basically defeated your dielectric. So if you put a polarized capacitor in there backwards and it's not protected, that sucker will blow up on you. Because all of a sudden you have current flow through a voltage, right? You understand? These guys they're hermetically sealed, and they will pop on you. I'll show you a video where these guys are popping them directly. And of course, the amount of current flow we get through these things would be determined by the voltage. So these things have what we call a working voltage. If you exceed that working voltage, then you're going to have a lot of current flow through the dielectric, and you're going to push that current through a voltage, and these things will pop on you, right? You understand that? But sometimes they pop. A lot of your electrolytics, one end is sealed with a rubber head, and it'll pop that rubber head out on you. If you ever see a capacitor and it's pulsed out, then you need to throw that away. And you can check these things with an ohmmeter. You can watch them charge. Except for the little bitty ones. The problem with the little bitty ones is they charge so fast. So a little bitty ones, if you use an ohmmeter, if you swap them around, they'd show infinity in both directions. You might see your meter blink because they charge so fast. Your big ones, though, you can check those out. Or you can use a big resistor. If you got a little tiny one, just hook a resistor in series with it and charge it through that. So what I got over here is I've got a capacitor. We'll come over here to the other side. And this is a 100 microfarad capacitor. And one of the two things we need to really, really look at is not only the capacitive rating, but we also need to look at the voltage rating. And I don't know if y'all can see this. I don't think I got enough to pass around. But this guy, if it focuses in, is 100 microfarad, 25 volts. So that 25 volts, if I exceed that, then it could do what? It could pop on. Or it could short, which is bad too. This is a polarized capacitor, so you know this is what we call a radial lead. And for some reason, on the radial leads, they identify the negative side. So y'all see this big old white stripe with all these negatives coming down. So that means this is the negative side, and this is the positive side. Are you okay? Yeah, well, you can't see the little minus sign, but that's the little minus. Yeah, y'all can. That's the little minus sign right there. So on the radial leads, what they don't identify both leads, because if they identify one, hopefully you know the other one is the opposite polarity, right? For some reason, on the radial leads, they identify the negative lead, and on the actual leads, they identify the positive lead. You know what we mean by radial and axial now, right? What does that mean? I'll say you. We're talking about pressure. We're talking about, so this is a radial lead. So radial leads, it comes out both sides. This is an actual lead. They come out like that. So actual leads, they come out the side, right? Radial leads, they come out one side. Okay there? So for some reason on the actual lead, they might have this lead labeled positive, right? You understand? On the radial lead, for some reason, they identify the negative side. They also do something different, but it disappears as soon as you cut the leads to put it in a circuit board. But when we're holding this thing in their thing, another thing that they do is they make one lead shorter. Let me put it against black. And you'll see this lead over here is shorter. And what lead is that? That's the negative lead. And that's also true on a lot of radial lead diodes. It's also true on radial lead LEDs. A lot of your LEDs are radial lead LEDs. If you ever look, and the cathode is going to be the short. So if I put this in a power supply, I need to make sure I understand the polarities. I need to understand I put this in there right? So what we're going to do is we're going to take this guy up. We're going to put this over here. And then I'm going to come over here and use, I'm going to use my 100K ohm resistor because we want to see it charged if I didn't do something with it. Okay. So what would 100K be? This is not a 100K. This is a yellow, violet, yellow. Oh, this one. So what's yellow, violet, yellow? So when you come up to me and you say, Rich, I need a 100 ohm resistor, you know the first thing we'll ask you? I'm going to ask you what's the color code. Okay, so be 41. Yellow, violet, yellow. Nobody's got that yet. This is embarrassing, guys. You ought to be embarrassed. This would be like driving a car. This would be like me saying, how do you turn left? And you're sitting there going, like SpongeBob. You ever watch SpongeBob? If you got grandkids or you got kids, you watch SpongeBob. Huh? 470K. Okay. This is a brown black yellow, which is what I want. And then I'm going to put it in series with my my capacitor. Now, what a capacitor does is when you got a battery fully discharged, it basically acts like a short circuit. So as soon as you put current on that thing, if you just put a voltage across that thing, it would pull a ton of current to start off with. And then the higher it charges up, the less current it's going to pull. But the voltage across to the battery would go up too, right? You understand? So what we're going to do is we're not going to look at the current. We could. But we know as the voltage goes up across the capacitor, the current in the circuit is going down. Everybody understand why? Because that sounds like that contradicts Ohm's law. Because we say, well, when voltage goes up, Current goes up, but it all depends. Yeah, it's true on resistors, but on capacitors, what happens, these things are charging. So I come over here and I'm trying to get to my marker. Oh, I gotta have my PowerPoint go. I can find my blank screen. Here's one. There was one. So we come up here, we have a capacitor. So what I've got a resistor. Then I have a capacitor. And it's a polarized capacitor, so I have it like that. Then I'm gonna come up here and put a 5-volt DC source. I gotta make sure I honor the polarity on my capacitor. Even though, guys, this wouldn't hurt it because we're protecting it with a 100K ohm resistor. It's just that you would actually see it not charged and you'd see current flow through it. So I start off, this thing's completely discharged, so it's got 0 volts across it. Understand that? So all the voltage, if this right here is plus 5 volts, Kirchhoff's voltage law says the sums of the voltage drop in a circuit has equal to the applied voltage. If this guy's completely discharged, it's dropping no voltage. So that means if I measure across my resistor, I should measure around 10 volts. Now, as soon as this charges the 1 volt, so my current in my circuit, we can't calculate the current in my circuit with the capacitor because we don't know its opposition, right? You understand that? But I do know that. So I would be equal to V over R. You don't have to calculate it. We're just going to notice this. So I would be equal to 10 volts over 100K. Now, when this sucker charges up to 1 volt, Kirchhoff's voltage law, that's not 10 volts, that's 5 volts, right? So Kirchhoff's voltage law says that sums of the voltage drops has equal to a circuit. So this guy goes up to 4 volts. So now my current flow would be, I would be equal to 4 volts over 100K. So what happened to the current flow? It went down, right? Okay. When this charges up to 2 volts, that means I got 3 volts up here. So what happens to my current flow? It goes down. This guy charges up to 4 volts. This guy goes to 1 volt. What's happened to my current flow? Okay. This charges up to 5 volts. This goes to 0 volts. What's my current flow? None. So a capacitor works like a battery when it's charging. If you ever looked at the current on a lead acid battery, you can't really do it on a NiCad battery. A lead acid battery is voltage charged. So if you ever put a resistor in series with it, it's going to have to be a big one. You put a source across it, you see it pulls a lot of a current when it's dead, and as the voltage goes up, the current that you need, the coulombs that you need to store in your battery don't need to be as much, right? You understand that? And this is the same thing true with a capacitor. So a capacitor in a DC circuit, when it's charged, it acts like an open. When it's charged, right? You understand that? And if it don't have a path to discharge. So what we're going to be able to see when I put my meter across this thing is we're going to be able to, when I put power on this thing, making sure I use the right polarity. And like I said, in this situation right here, we would probably be okay because we're protecting it with a 100K ohm resistor. In power supplies, guys, we are not protecting this guy at all. The only resistance in the circuit is the resistance of the transformer. So in a power supply, the capacitor charges almost instantly. It charges with the sine wave. With the pulse. So I'm going to look across my capacitor. Okay. We're going to watch it charge, but you got to understand across the resistor it's doing just opposite. I need to spread this out a little bit because my two leads are very, very close together. I know y'all want to see what I'm doing. Oops. So here's my circuit. I've got the negative lead, so I'm going to take my power supply. I'm going to make sure I put my negative lead on my power supply towards the negative lead of the capacitor. I'm going to take my positive lead and put it toward the top of the resistor because we're charging through the resistor. I'm going to come up here and put my meter, hopefully, so we can see it. Is it okay if it's upside down? I can see. I've got it on volts, DC volts. I'm going to turn it on. And right now, the capacitor is basically discharged. I'm going to turn this on. And what's it doing? Now notice it started out charging real fast. But as the charge goes up, the voltage drop across the resistor goes down, the current goes down, which means it starts charging slower. So the closer it gets to fully charged, this guy's going to charge real slow. And then it should charge up to what? Should charge up to 5 volts. Mathematically, it never does, but it does in real life. See, it's slowing down. Because why? Now the resistor is dropping so little voltage, the current flow, and how fast you charge it depends on how fast you can push that current in there. So it's charging. And what's it going to charge up to? 5 volts. But according to mathematics, it won't. It never gets there. Okay, so it's charged up to 5 volts. And of course, I'm going to come up here and disconnect my power supply. So it's disconnected. And of course, now it's going to discharge through itself. But it's going to be real slow, right? Now, if I turn my power supply off, it will discharge through the circuit. Guys, this is what we use for the memory in this computer. It uses what they call a dynamic memory, and it's nothing but billions of little capacitors that we charge up to store 1, we discharge them to storage 0. But we have to have an electronic circuit, we call them refresh circuits, that automatically goes out there and refreshes the memory at a constant rate. So it keeps your zeros a 0 and your 1's a 1, right? You understand? And dynamic memory is so much cheaper than what we call static memory. Static memory takes about 5 transistors per digit bit. Dynamic memory takes 1. So we can get billions of more storage cells on a dynamic than we can on a. So we okay? So I can hook it up to the power supply and it should charge back up. But if I hook it up, and I know it's past time for break, guys. So I'm going to turn my power supply off, so it's going to discharge back through the circuitry in the power supply. So it should start discharging pretty fast. But the closer it gets to 0, right, the slower it's going to go down. So we can store a charge in these things, right? You understand. And then, so what we're going to do is we're going to use a capacitor. We'll start off with the positive power supply. We're going to charge that sucker up with the pulse. And then when it starts dropping down, the diode turns off, and we're going to run the load through the what? Through the capacitor. So, I'll get back, we'll show you all the basic formulas that we use. They're not real hard. Anybody that's had AC, y'all probably heard of RC time constants. Pi has nothing to do with R times 6. 5 times, yeah. But we don't need to use that because we're never going to fully charge it So we're not going to use 5 times because it only charges once. It only charges once on the peak, and then after that it discharges. So it never tries to discharge completely. So what we'll use is we'll just use R times 6 because we're never going to discharge it below to 63%. And the problem I have is my computer moves around, and I can't leave it plugged in all the time to upload these lectures. So I'm teaching classes in different buildings. It don't like something, guys. So the capacitor charges and discharges at what we call an exponential rate. You'll know with exponential, it charges in a common log. Natural log. Y'all know about logs, right? Logarithm. You okay with that? Well, we have two types of logs. We have what we call a natural log, and we have what we call a common log. A natural log is what we use to work with things that vary in curves, an exponential curve. Common logs are just 10 raised to some power. So the log of 1,000 would be 10 to the third. So that's how easy that is. 10 to the third. Yeah, so the log of 1,000 would be 10 to the third. Then what we do to allow us to round a little bit is we multiply that by 10 and we call it dB. So the dB of 1,000 would be 10 to the third. I'm sorry, 30th. So we'd say 30 dB. 30 dB. Y'all heard of dB before? I haven't heard of dB.
Yeah.
It's called decibels. So technically, I'm going to do something my computer don't like me. Is basically a log deals with dB. And a common log 10 to this. And technically, it's got the name as a bale. I don't know what it is. So the log of 1,000 would be 3 bales. Does that make sense? So what they did to give us the ability to round, but we might end up with a real big number. So somewhere on your key, you got a log key, right? Calculator. So I might have to close this out. And if you enter 1,000, it should come up and hit your log key. If you got it on common logs, it should come up and say 3. Does it? Yeah, we call them reverse Polish. So what we do is we have a strange number. So let's take the log of 1,038. 1,038. What's that? 3.1. Stop there?
No.
Okay. So this is the problem we're having. 3.0 what? Let's just take it out. What's that?
1,617,7,3,5,4.
So if you don't round that off, you could literally raise 10 to that power. But when we use milli and we use micro and those kind of, we round to a certain decimal point, right? So what we do is we want to round this. So what they did, they came up with a method where I multiply this by 10. If I multiply it by 10, we would just move it right over there. And then we either leave it alone and but if we move it by 10, we don't call it bales anymore. We call it decibels, which would be dB. And then we round it. So I might round this to, 3.01. 3.02, and then I would say dB. So they either round it to 30, 30.02 dB. Now what it does, it's basically just like we use engineer notation. What do we use engineer notation for? To represent very large, very small numbers with few digits. That's what we use engineer notation for, right? And we always round, right, if it don't come up to be equal. Everybody understands? That's what we use dB for. And we use it to represent very large and very small numbers, right? You understand that, with very few digits, right? So it would be a lot better for me to say, 30.02 dB than 1038 or even, Wales. This is what we use dB for. If it's a minus dB, then it's a negative. If it's a positive dB, it's a positive. So if you take 30 to the minus, you see it'll come up to be 0.001 something. But anytime you round, that means if I was to take 10 and raise it to this power, then it's not going to be as accurate, but it's going to be accurate enough, right? Guys, if you ever get into audio or you ever get into communication, you're going to deal with dB. So these are used predominantly in electronic communication. They call dB loss. You have so many dB loss. You have so many dB crosstalk. If you ever really get into stereos, you're going to run into that. Okay. R is equal to, T is equal to R times C, right? So, half wave, if it's 60 cycles, then that's probably what we use. And you can see the higher the frequency, the shorter time it has to collapse, right? You understand? So the shorter time the thing has to run the load. So it means I could use smaller capacitors if the frequency was greater than 60 hertz, right? You understand? So this is one of the things a switching power supply does, is it comes up and re-oscillates it at a lot higher frequency, like 50K. And now my capacitors can be what? Small, because they don't have to run the load for 8.3 milliseconds. If it's full wave. If it's full wave, if it's half wave, then that capacitor's got to run the load for 16.7 milliseconds. Because it's got to make it to the next alternation, right? You understand that? If it's full wave, which they don't show it, then the capacitor's got to run the load for 8.3 milliseconds. So that means on full wave, we could probably use, if I want the same pulse, I could use a smaller capacitor, right? That makes sense? Everybody okay? Y'all know where those times came from? If you don't know, you don't know. Reciprocal of frequency, yeah. So the time would be equal to 1 over L. And that's the time for a cycle. Yeah, so the time for 60 cycles would be 1 over 60, which would come up and give me 16.666666 milliseconds. So we'll just say 16.7 milliseconds. But what we're doing is that's the time for a watt. That's a cycle. So on a half wave, that right there would be a cycle. Right, you understand? Would be the same cycle as the input frequency. Now on full wave, this is the cycle for my input. So this right here would be 18.7 milliseconds. But my capacitor don't have to run it. I'm sorry. So this would be the next positive. So this would be the next positive, right? So that would be 16.7 milliseconds right there for the next positive pulse, right? But ours on the input. But what we're doing is we're taking this guy right there and we're doing what? We're moving it up to the top. So that means the time between these pulses are going to be what? 8.3 milliseconds. So the pulsating frequency for half wave is the same as the input. The pulsating frequency of the output for a full wave is 1/2 the input. I'm sorry, 2 times the input. Y'all going like this, even though I made that mistake, right? So that means if I've got 60 cycles half wave, my pulse frequency is going to be 60 hertz. If I've got full wave, my pulse frequency is going to be 120. Y'all understand that? Because what we've done is even though this is one cycle of my input, right? You understand? What we're doing is we're getting my output frequency is going to be twice my input frequency for what? For full wave. And that comes into play. So that means here the capacitor would have to run the load for what? 16.7 milliseconds. On a full wave, the capacitor would have to run the load 8.33 milliseconds, or 8.3. So that means if I use the same capacitor, I'll get more out of a full wave than I do a half wave. Are we okay? So we call this a ripple frequency. So the ripple frequency for a half wave is going to be exactly the same as the input frequency. The ripple frequency of that ripple voltage for a full wave is going to be twice. And this is one way you tell if you've got an open diode. You can tell with an oscilloscope just like that. So if you look at the output, it's supposed to be full wave, and you measure the time between those pulses, and it's 16.7 milliseconds. It means one of your diodes is open. If you measure it and it's 8.33 milliseconds, it means your load is probably pulling way more current than the power supply was designed to handle. And so what you're doing is you're exceeding the specifications for the diode, for the circuit, right? So when we say regulation, we mean it only regulates over the span that it was designed to regulate. So a regulator cannot regulate infinite currents, and it cannot regulate infinite voltages, right, without them damaging. So one of the things that you need to understand is that when you design these things, it's very important to understand the specifications of the devices that you use. Well, okay. Are y'all beginning to zone out? So this is our average voltage right here. Our average DC voltage is going to be right down the center of this pulse. Because the negative part is the same and your top parts are the same, right? So basically they cancel each other out and it puts the reference right down the center. So that's going to be my average DC out. So what would be the formula? So what's this right here? This is V peak out. So that's what we're getting out of our diodes, right? This right here would be V ripple peak peak. So my DC out, volts DC should be equal to V peak out minus V ripple peak peak divided by 2. So we can't calculate. Y'all understand why it's divided by 2? Yes or no? Because it's down the watt, down the center. So all we got to do is figure out how to calculate watt. We know how to calculate V peak out. It's just what? It's V peak secondary minus the diode drops. It's no longer, right, V peak out minus the what? The diode drops. You're thinking about it from the RMS standard. We're looking at V peak. So how would we come up with a voltage out of this formula right here? Yeah, how do we get voltage out of that formula? How do we get a V into this formula? Because that's what we got to do. We got to calculate voltage, right? So what does ohms say that R is equal to? R is equal to what? V over I. If it's equal to it, it means I can replace R with what? V over I. So I could change my formula over here. I could say T is equal to what? V over I times C. Okay? So I need to transpose the formula and solve for V. And this is going to be V ripple peak. And that's what a lot of people don't see in their mind. Ohm's law says that this is equal to this. So if it's equal to it, it means I can do what? I can replace it, right? You'll understand that. So it means I've got 4 quarters is equal to $1. So you're at a counter and say, well, that's $1, right? And you say, well, I don't have $1. And you got 15 quarters in your pocket, right? Because I can replace what? $1 with 4 quarters. So that's what we're saying. If Ohm's law says R is equal to V over I, anytime I see R, I can replace it with what? V over I. So since it's time, we could actually put the C up on top, right? VC. So this would be the side. This would be the V peak out, right? This would be the size of the capacitor in farads. And then all I have to do, since T is on over here and I is over here, all I have to do is just swap them. So now I'm sorry, we're solving for V. So we have to flip them around, right? So V, we would move time over here, right? Everybody okay? Now flip them over. So V would be equal to I times T over V over C. So we got I up here. Time is up there. We're taking V and putting it over there, so that'll be over C. Is that right? So what would I be equal to? It's going to be equal to the load current. What's T going to be equal to? But what time? We'd use 16.7 milliseconds for full wave. We would use 8.3 milliseconds for half wave. And then C is going to be whatever capacitor you use. Now another thing we can do, I know that time is equal to 1 over L, so we could use this formula right here. V ripple peak peak would be equal to 1 over C times L. And now you say, okay, half wave is going to be the same, full wave is going to be double. Y'all see what I did? Yes or no? So I just flipped it around because frequency is equal to 1 over time. So that's the basic formula, guys. So it determines on how much current we're going to run through our load, right? You understand that. So you got to know the load current. So there's the formula. I of the load divided by C over F. You can use I of the load, but I didn't even look at this because I used the basic formula. Time is equal to what? R times C, and then I just rearranged it to solve for P. So I of the load. How do we do I of the load? Well, we're going to guesstimate it, and what are we going to do? So if I got this guy right here, and then this is the last thing we'll look at. I got my diode, and then I got a load over here. And let's say we get my V peak out is equal to 5.6 volts. And then this right here is a 1K. Well, if you notice, there's so little difference between V peak out and this right here, then to get a guesstimation of what the load current is, we just use V peak out. So I'd say V peak out would be equal to approximately, I of the load would be equal to approximately V peak out over R of the load. And that's a guesstimation. The only other option I got to do is to measure it. So I calculate it using V peak out over that, and I calculate, 1 milliamp. I go out there and measure the current, and it comes up to be 90 milliamps. So it's just not enough to worry about, right? What we're trying to do is say, we're trying to get an indication whether the power supply is what? Good or bad. And then I know the size of the capacitor. If I know the size of the capacitor, I know the current. I know it's a half wave, so if it's a full wave, I would use 120. If it's a half wave, I would use what? 60. Now I don't have to remember 8.3 milliseconds. I don't have to remember 16.6 or 16.7 milliseconds, right? You understand that? So a half wave, the pulsating frequency of that ripple is going to be the same as the input frequency. For a full wave, it's going to be what? Double. Now, of course, when you design this, you're trying to size the capacitor. So this is the formula for sizing the capacitor. So when you design a power supply, what's the two main things you're looking for? So when I look at this power supply right here, what's the two ratings, the main ratings on that thing? Huh? Y'all haven't ever looked at y'all's power supply before? The input voltage, the output voltage, and the maximum current it should put out. So that's the two things you're looking at when you design a power supply. How much input voltage are you going to put into your transformer? How much you going to get out? And how much what? How much current that dang load is going to handle. That's, huh?
So they use 220, and the guy put it up, and turned them on, so that high insulin burned them up. They didn't check to see if they could set the 220.
The problem on our P3 airplanes, they had power plugs on there, and they used 120 volt plugs, but they were 240 volts. So you could plug, and them guys come in there and they wanted to carry flashlights, and they plugged these rechargeable flashlights on them, and they caught on fire. And for some reason, you don't want to be on a plane when there's a fire on it, right? And the gripe, cockpit fills with smoke. That plane is down until you figure out what it was. Now, the pilot had a little old tiny hole up in the access pack in the top, and they could pop it open. And buddy, it's pressurized, and it'll just suck all that air out. It was really neat. They had a vacuum cleaner that they'd hook up to that thing. It had a filter in it, and that vacuumed the plane just by using the pressure differential between the inside the plane and outside. But yeah, they had that smoke bin up in the cockpit for obvious reasons. You want your pilot to be able to see too, so. Yeah. They could pop that thing on, man, it'd suck that stuff out of there like crazy. And it didn't suck them out of their seats, by the way, because it was so small. But you see those movies where it sucks a guy through a hole that big. Of course, that it was that lady that got almost sucked out when that jet engine came apart, but it busted out a window, right? So it's pretty good stuff. So everybody okay? So y'all need to make sure, hopefully you should have your lab books. Where did you get your lab book at? DC. And I don't forget which lab it is. So we're almost ready to start working on a couple of labs. We'll try to do that, start into that next Tuesday. We'll go over the lab procedures because I have pretty strict lab procedures, so everything goes right and it makes it easy for me to grade and y'all don't get hurt, right? You understand that? But y'all know we gotta wear what? Got to wear safety glasses. Make sure you get side shields on. So I've had people say, well, I got regular glasses. I wear regular glasses cutting my grass. And I get stuff in my eyes all the time. I do. Because it just flies up and comes up through the side, right? So, of course, I need to get me for some prescription safety glasses. Which I have from U.S. Steel, but they're not. Yeah, they're okay, but they're not. So everybody okay? Got any questions? Pretty neat stuff. So what we should do is hopefully by the time we get out here, you should be able to set you up a linear power supply. And it's always nice to have one. Why? Because that way you can do labs at home. You can start playing around with electronics. What's nice about electronics? It might not only be your career, it could also be your hobby. I can't tell you how much stuff I burned up and figured out at home, not at school.
With all the dead TVs, I probably could have fixed myself.
I fix a lot of TVs too. You can't fix them now.
Can't fix TV now?
You don't hardly see any TV repair. Used to, when everything was tubes and transistors and everything was discrete components, you had TV repair places all over the place.
Some big fat back TV?
Yeah, well, the CRT TVs. But now that we're using LCD, they draw such a little current. Usually when you decide to replace your TV, it's because you want a new one. So these guys here last so long. You need to make sure you plug that thing in some type of a power strip that's got a suppressor on it, by the way, because we're notorious in the state of Alabama for lightning storms, right?
So what I'm saying, when the lightning storm hits, usually there's a power supply that's probably going to, right?
Yeah, if it's external, most of them now, most of your new LCD screens, the LED, they're still LCD, it's just they're backlit with LEDs. Most of those have a power supply. Almost, they look, of course, they're bigger.
You don't think you can go in one of the newest TVs to fix the power?
You might, but most of them use these switching power supplies now that are not, they're too hard to repair. But it's still cheaper to replace that than it is to do what?
Right.
But, yeah, and you can't get used to, there was a company called Sam's Photofax. I don't know if y'all remember Sam's. They put schematics out on everything. Now what companies do is if you're a repair facility, they make you sign a non-disclosure agreement that you won't give out the technical information. If you give out the technical information, then you could lose the ability to repair those things.
It took my grandma forever. She had this big 4 TV, like, she just got rid of it.
I had a big projection TV. I mean, a big projection TV. That was the first big screen TV. Was actually, yeah. So you had, basically it worked like this overhead projector, but it had 3 different color bulbs in there. It had a red, green, and blue. And those things would get out of alignment. I wonder if your bulbs would go out and now all of a sudden people would be strange colors. Now you could fix those. You could pop the back off and find the bulb, and you could buy the bulb and replace them.
Yeah, I was trying to fix it.